I think that it's going to be quite a shock for people that are really beginners in Faust, because I'm going to speak about the Faust compiler quite in technical detail, so to speak. But well, I hope that I'm going to be clear enough for everybody. So the title of the talk is Where is Faust going as a programming language? ? It's also Romain that suggested that title. Obviously, we have some ideas about where we are going with Faust. But I would like to quote Pierre Dac about forecasting the future, so to speak. So Pierre Dac used to say, let's see if I can move my slides. Okay, it used to say, the future is difficult to predict, especially in advance. So I don't know how familiar people are with Pierre Dac, but it's a French philosopher with many quotes. He was someone saying about the weather that it's better to have rain today than on a sunny day, for example. Well, I hope to appreciate this sense of humor. Why I say that? Because because it's difficult to predict what's going to happen, how Faust is going to evolve. And I would like to start by presenting two extensions of the Faust programming language that we tried, and we decided not to poursuivre. Do you say that in English? Pursue. So these two attempts were Multirate Faust and the enable primitive. So I'm going to present these two extensions, and you can think of them as an introduction to the third extension that I'm going to present, and that hopefully will be the right one. Okay, so Faust Multirate we wrote a very nice paper with Pierre Jouvelot from École des Mines of Paris about this Faust Multirate extension. It was entitled Dependent Vector Types for Data Structuring in Multirate Faust. And basically it presented all the theory of this extension. So I'm going to, it has all the type system, blah, blah, blah. And so it was quite complete from the theoretical point of view. So I'm going to present the ideas of this extension, and then briefly explain why we decided not to continue in this direction. So basically, this talk is about some of the failures we had, or I had, in developing Faust. So the question that try to solve Faust multirate is, how can we introduce multirate and multi-dimensions in Faust? And the idea was to use a very minimal extension of the language with just basically 4 new operations: vectorize, serialize, concat, and access, as well as extending all the primitive operations to operate not only on signals of numbers, but also on signals of vectors, of matrices, etc., etc. So I'm going to explain how this was working. So the first operation was vectorize. The idea of this vectorize operation is to take an input signal and then group together the samples to produce an output signal, which was a signal of vectors with a rate which was, in this example here on the screen, 1/3 of the rate of the input signal. So vectorize was an operation both to create structure and also to change the rate of signals. So the reverse of Vectorize was the Serialize operation. So it takes, for example, a signal of vectors and it creates a flat version, so to speak, of this signal with a rate here which is 3 times faster than the input signal. So basically, Serialize and Vectorize were able to maintain the flow of information, but changing the rate for the vector size, so to speak. Then you add 2 additional operations, like the concatenation of vectors, and a 4th operation to access elements of the vectors. And that was basically the idea. And by combining these 4 operations, you were able to write multi-rate, multi-dimensional code. So why did we decide to abandon this approach? First of all, we don't really need in Faust vector operation because we can express them. And it turns out to be a complex system, especially it was complicated to, it was very easy to express Faust programs that were not correct. Obviously, the type system was able to detect that the program were not correct, but nevertheless, we thought at some point it was too complicated, even if at the beginning we had the impression that it was quite simple. Because the vector operation were not really needed, because we can express them in Faust, we decide another approach, which is based on a new primitive called enable. And this enable primitive was able to enable and suspend a computation. So let me try to explain the idea of enable. Let's say that you have, I don't know, a reverb, for example, here, and that you want to mute that reverb. A way to do that is to multiply the inputs and the outputs of the reverb at the same time with a fade out signal, a kind of envelope signal that goes to 0. So the idea of enable is to say, okay, this is what I want to do to suspend a computation. Why not have a special multiplication such that when the Y signal is 0, it tries not to compute what produced the X signal. So this was the idea of enable. Semantically, mathematically is a simple multiplication, but when Y reached the level of the value of 0, then it tries not to compute what produced the X signal. In order to do that, we had to annotate every sub-expression with the condition of when this expression was needed to be computed. So for example, let's say that in a big expression, we have these 2 enables here, that this signal here is computed by this pink expression here, this one by this blue expression. So the pink expression must be computed only when Y is different of 0 and not when Y is 0. And the blue expression needs to be computed only when Y is different from 0. So imagine that we have a common sub-expression. So now this common sub-expression is computed only when this more complex expression is true. And maybe you have also sub-expressions that are both part of an enable chain and used without any enable. And in this case, they must be always computed. In other words, you start to, if you have one of two enable, it was okay. But as soon as you start to use many of these enables, really to have a very fine control of when things are computed or not, you had a kind of explosion of conditions, and somehow you start spending more time at evaluating the condition than the actual expression itself. Again, it was very complicated to use that right, and also we must say that the semantics is super ugly in this case. Why is it ugly? Because the expression that goes into that produces a signal that goes into an enable, you don't know anymore what this expression is really doing, because the semantics doesn't only depend of the component of this expression, but also of the surrounding environment, and this is really ugly in terms of semantics. And again, it was very difficult to master for the reason I just explained. So we decided also to stop this. Not to stop, because it's actually part of the Faust compiler. So if you want to use it, you can use it. But we never really make publicity about this primitive, as it is not. We don't recommend it anymore. Okay, so this is for what we decided not to do, and now I'm going to explain what we are going to use to enable a control about when computation are done or not. Okay, so what is the future? Well, one of the elements of this future is called on-demand, and I think it's the right way to approach this problem of controlling when computation are done or not in a Faust program. The difference between these two previous approaches and this one is that the two previous approaches were based on operation on signals. So we had this Vectorize and Serialize, which were operation on signals, and the enable is also an operation on signals. But actually, Faust is not a programming language to describe signals, but it's a programming language to describe signal processors. Obviously, these signal processors are used to create signals, but the language itself is a description of an audio circuit, so to speak, of a signal processor. And you start by composing elementary signal processors like operation like delay, multiplication, etc. You have a functional language to algorithmically build complex audio circuits. You can also use pattern matching to do that. So Faust is really a language to build audio circuits, to build signal processor, not signal directly. So it's a subtle difference, but this new on-demand primitive is a primitive that works at audio circuits level, not at signal level. So basically, it's a new operation that takes any audio circuits and turn it into an on-demand version. So let me explain what is this on-demand version. So let's say that you have a signal processor P here. What happens if you use on demand of P? You create a new circuit with an additional input here, H, which is a clock that controls precisely at sample level when P is going to compute or not samples. So the clock here, it's a signal made of 1 and 0. When the signal is 1, the computation is done. When the signal is 0, the computation is skipped. So I don't know if there are super collider users, but it's not very different from the demand-driven computation in demand rate computation in super collider. So let's say that you have this expression here, which is we take two input signals, we multiply these two signals, and the result go into the abs function to produce the final result. Let's imagine that it works using a demand. So abs receive a demand saying, okay, give me the next value. Okay, abs goes to the multiplication and say, okay, give me the next value. The multiplication go to the input signals and then just sample the two input signals, compute the value, send it to apps that send it that produce the final result. So in this demand-driven computation, there is a kind of loop. You start with asking value. This demand is propagated until you reach the audio input signals, and then the result is propagated back. So if you do that like this, it's super inefficient. And the semantics is quite complex to express. But fortunately, there is a way to do that in a very efficient way, with a very simple semantics, which is described here. So what does on demand? Basically, it so you use the clock signal here to downsample the input signals. Then you process the downsampled version of the input signal with P. It produces some output signal, and then you upsample the output signals to produce the final result. So you keep the same semantics from left to right, so to speak. You use conceptually, you do demand-driven computation, but it's implemented like normal, regular computation. So the key observation is to see that demand-driven computation is normal computation operating on downsampled signals. So here it's the way it works in more formal ways. So if you are not used to this kind of notation, these are called semantic brackets. It's a way to differentiate the syntactical aspect of an expression from its meaning. When we use semantic brackets, it means that we want to speak of the meaning of an expression, not its syntactical structure. So here, what do we say? We say that the semantic of a on-demand processor is a function that takes a clock signal and some input signals, but it uses the P processor here, applying it to the downsampled version of the input signals to produce the output signals, the Y here, and these output signals are upsampled here. So now we have to understand how we downsample and how we upsample the signals, but you see that the semantics of on-demand of P is completely described once you know the clock signal and the semantics of the meaning of the signal processor P. Here's the semantics of downsampling and upsampling. I introduce here these two functions, down and up, but it's going to be more clear in the next slide. So here is what happens. So you have the S1 signal that you want to downsample using the S2 signal. So basically, this S2 signal is a clock signal with 1 when you want to compute something and 0 when you don't want to compute something. So you use the downsampling is basically a way to select some of the samples of S1, not all. You only select samples when S2 is 1. So basically S1 downsampled to S2 will be A, then D, then F. In order to compute that, you can compute the down function of S2, which is basically where are the ones in S2. So the first one is at position 0, then the second one is at position 3, and the fourth one at and the third one at position 4. So basically down of S2 is just the list of the indices where S2 is 1. And you can express the semantic of downsampling by this formula here. So basically you index, you use down of S2 as index of S1 to create the downsampled version of S1. For the upsampling, it's the reverse process, so to speak. So it means that every time you have a 1 in the clock signal, you change you take a new value in the upsampled version. Every time you have a 0, you repeat the previous value. Okay, so it's upsampling a little bit different than upsampling done in the normal upsampling in a signal processor. But if you multiply the upsampled version with the clock, then you obtain what you do traditionally in signal processing. And again, you can do that by just computing the indices of S1 that you are going to use for the upsampled version of S1. So here we are using the value as index 0, so which is A, then the one at index 1, which is D, then the one at index 2, which is F, etc. So this is how you make the upsampling. Okay, so I'm going to make a kind of demo of how the system works. Unfortunately, we don't have a real version of the Faust compiler that use on-demand. It's a version of the compiler that generate pseudo code. And so I'm going to show you how it works, both by producing block diagram like this one and by producing graphs like this one. So the block diagram, you are already familiar with that, but it's extended with this on-demand. So here, for example, you have a noise generator, that run inside the on-demand. And here is the resulting graph of instruction. So the concept of instruction is a new one that is needed by this on-demand. And the idea is that instructions are in between signals and real instruction in an imperative programming language. And that these instructions have dependencies. And so the graph that you can see here, it's the graph obtained by drawing the dependencies between all these instructions. You see that to produce the output signal, it depends on this instruction, that depends on this one, etc., etc. So you have a graph. What I'm going to do is to explain the structure of these instructions, because of the on-demand now, every computation appears in a time frame, in a specific time frame, and so we have to. You see here, for example, when I scale 0, then you do this instruction. So most of the instructions now have a kind of condition which is related to all the englobing on-demand of this instruction. So this is how the Faust compiler works. You start with programs. These programs are algorithmic description of an audio circuit. And so there is a first phase where the user program is executed and it produces an audio circuit. Then there is a phase of signal propagation into the circuit. So in order to discover how the outputs of the circuit are computed according to the input of the circuit. This gives a first representation in terms of signals. These signals are transformed into instructions. Then these instructions are scheduled. Then you have different backends for the different programming languages that are supported, and then imperative code in these different language is generated. So I'm not going to explain all these steps, but only what are signals and what are instructions. And once I've done that, I will do a kind of demo. Okay, so what are signals? So basically, signals are numbers, user interface elements, as Romain demonstrated, input channels, recursive definitions, operations on signals. So here, instead of saying that we have plus, multiplication, absolute value, etc., I just have one star generic operation, but it doesn't really matter. So then you have delays, downsampling, and upsampling. So these are basically what a signal is. So one of the steps in the compilation will be to translate these signals into instructions. In this process, recursive signals, delay lines, upsampling and downsampling will disappear, replaced by memory access. So here it's a memory signal. So a memory signal is a signal, but using a simplified representation where we use memory access to retrieve information computed from other signals. So you don't have delay lines anymore because we are going to implement delay lines using tables. You don't have recursion because we are going to implement recursion using delay lines, etc., etc. So it's a signal, but where the computation use memory access, do a computation, and store the result into a memory. So in order to describe this, we need also memory destinations. So memory destinations are output signal. Then we have time variables where we store signals that represent clocks. Memory where we store scalar signals, and vectors where we store delay lines. And now, what is an instruction? It's a combination of a memory signal, so a signal expression using memory, that is stored into a memory destination, here, here, or here, and that is only computed when it's this time reference indicate that it must be computed. So now every instruction has a time reference. And so what is a time reference? Basically, it's a list of all the clock signals in the surrounding environment of an expression. Okay, let me try to make a demo. So I'm going to quit the slides here. So I need to stop this sharing, and oops, okay, and I'm going to share another okay, so here it is. Can you see the new screen? Okay. Okay, so this is the simplest Faust code you can imagine. Process equal underscore. So it's basically a cable. You just copy the input to the output, and this is the corresponding pseudo code. Okay, so what I'm going to implement is a first example, which is going to be a sample and hold. So, clack. Okay, so this is the way you can implement a sample and hold in Faust. You use a select2. This select2 is a primitive that takes a control signal, which selects which of the two inputs will be reproduced at the output. So when the button value is 0, then it produces this, the first this input here, and when its value is 1, it selects this input here. So when it's 1, it selects the real input here. And as soon as it's 0, it just selects the feedback signal. So it maintains it holds the previous value. So it's a sample and hold, but you see that to do that in Faust currently, you have to use a recursion, a loop here. And this is the code generated by this expression. So basically, you maintain always the previous value, and as soon as the button is pressed, you select a new value from the input. The nice thing about on demand is that a sample and hold is just on demand of underscore. And I don't know you, but I find this very elegant. Okay, so let's compile this example here. Okay, so you see you have on demand of underscore, just so on demand of a cable. And you see the code here, it said that whenever the button is pressed, it's 1, then you sample the input. So you don't have to make a recursion, it's simpler. And again, I think it's quite elegant. So let's do another more complex example. So I want to produce a noise. Okay, so this is a noise generator. It uses a recursive, so you have a pseudo random number generator, and you map these random numbers between -1 and +1, and it creates a pseudo white noise generator. Let's say that I want to control with a button when I choose a new value from this white noise generator. So I can write this like this. So basically I do a sample and hold of this random number generator. But you see here, so this is the way you do that currently in Faust. In the way it is done here, the noise generator is always computing. And when you want a new random number, you just sample the current value of the noise generator. With on demand, you can do something completely different, which is really to step into all the value of the white noise generator. So let's try that. So here it's how you write this. You say, okay, I connect my noise, my button called noise, into the on demand of the noise generator. So here's the code. So you see the button noise, the on-demand circuit, and inside the noise generator. And here is the way it's translated. So what's interesting here is that you really control when a new number is computed. It's only computed when the clock's input is at 1. So it means that if you want to have several noise generators, let's say that I put in parallel 3 noise generator with on demand with a button called noise. If I do that, then here is what we have. So we have the 3 noise generator, and they are controlled by this button called noise. Because the button is called noise in the 3 cases, we don't have to compute 3 times the noise generator because it's going to be the same. So this is what you see here. It's computed just once, and it's copied into the 3 outputs. But if we sophisticated a little bit the code here, instead of having the same button, we have 3 different buttons. Then you see that because each noise generator is going to run in a different time frame, it's going to be a different noise generator. So this solves the problem that you have in Faust, that if you want to have different noise generator, it's a little bit complicated. You can do that, but using on demand, it's much simpler to do that. So basically with on demand, you can go into a more compositional oriented approach. Faust will never be a composition language, obviously, but you can, by controlling when computations are done, you can go a little bit more in that direction. So I think that was the last example. So I will switch back to my slides. So arrêtez le partage, stop here, and now I'm going to share again the slides. So, so I would like to. Okay. So I'm nearly finished. What I would like to say that this on-demand primitive is very interesting because you can use it to implement some related operation. For example, upsampling. If you imagine that the clock signal, instead of being only 0 or 1, can be any positive integer, then you can do upsampling. For example, if the clock is always 8, you will run for each sample. You will run the audio circuit 8 times. So you can do upsampling that way. You can also do downsampling. The difference between on-demand, upsampling, and downsampling is that is the fact that inside upsampling and downsampling, you can compute the sampling rate, a correct sampling rate. If you are just using on-demand, there is no way you can really compute a sampling rate. So you use a default sampling rate, but it's useful if you do filters, for example, inside an upsampling to have a correct upsampling by 8, for example, have a correct sampling rate actually multiplied by 8. Okay, so so this is just what I just explained about upsampling and downsampling. And the third interesting primitive is interleaved. So the idea is that, I don't know if you are familiar with the super nice FFT implementation in Faust done by Julius Smith. So it's a recursive fractal, I don't know how to call that, implementation of the FFT. It's super nice. It's done with very few line of codes. And you end with an audio circuit with a power of 2 inputs and outputs. The idea of interleave is using more or less the same approach than on demand to be able to interleave the inputs and outputs of an FFT, for example. So imagine that the you have the input signal here, and the samples are distributed on all the inputs here. Then after n, every n samples, the computation of P is done, and the outputs are interleaved to produce the output. So this is a way to this way, you don't have to use vectors like we were thinking of in the first, in the 2011 extension of Faust, just by using interleave. Okay, so this is basically what we are planning. It's with on-demand. There are other things that are going on. Stefan will present many things that are related to the ecosystem of Faust, of the various backends. Recently, we opened the compiler, so you can the signal I mentioned, you can use them directly with an API, which is convenient to use the Faust compiler, maybe with other programming languages. And also, I think that someone will present Cifala, or maybe Romain. And in this Cifala project, where we, the idea is to be able to program FPGA circuits using Faust, we need to work on several interesting extensions. The first one is to use fixed point code generation. Because on an FPGA, if you can use fixed point operation, you save a lot of silicon compared to using floating point operations. In order to do that, we need to extend the analysis inside the Faust program. In a Faust program, we analyze all signals to compute the interval of the value that this signal can take, the minimum and the maximum value of this signal. So we add to that the precision, and by knowing the interval and the precision, we are able to generate. We will be able to generate fixed point code generation. Another thing that we would like to develop in Faust is loop re-rolling. So you are probably familiar with loop unrolling, and loop re-rolling is doing the reverse, having things separate to make them into a loop. So I'm not going to detail that, but it's probably going to be very interesting in terms of efficiency of the code for FPGA, but also for regular CPUs. And we are also working on direct VHDL code generation for FPGAs. Okay, so I think this was the last slide. And do we have time? Yes, we have a few minutes for questions, if there are any. I hope that it was quite clear. And so I can answer questions if there are any.
Yes, Yann, can you hear me?
Yes, not very loud, but I can hear you, and I can turn my volume here.
Okay, what is it louder now? Okay, I guess no and no. Okay. Is it better like this?
Yes.
Okay, cool. So is there still the echo?
A little bit, but less than before.
Less than before. Okay. So then we'll see it's better. Well, thank you so much, because I think that was very useful for everyone. You know, I think people were actually looking forward to this presentation. There were questions in the chat. So maybe we can do is we can take like one question after the other one from here, and then one from the chat, you know, like, or what about we do it? So maybe we can start with a question from here, and we have a questions from James, and I'm just gonna give the mic so that you can hear what he has to say.
So is it possible with the interleave to do somewhere where you have a hop size that's less than the size of the T? Like if you or make it a window.
Yes, well, yes. basically, all these primitives are designed to, in order not to require any signal processing semantics, so to speak. So what I mean is that if you want to have windowing on the input signal, then you will implement that by taking the signal, you feed an interleaved FFT, and before that, or inside that, you do the windowing. And then you, again, you do that, but on a delayed version of the signal. So by doing, for example, 2FFT on the signal and on a delayed version of the signal of half the number of inputs, you can, am I clear? Or?
Have any questions on the chat? There were a lot of questions, but you might have to repeat them because, or maybe
the echo is back.
I think no, it makes sense. You know, because like there's audio on your side and audio on our side, so maybe white. But
I'm trying to cut my mic.
Is there still echo when Yann's mic is off? Okay, yeah, apparently it's still there. Okay, so I'll try to fix during lunch break. Like, is there any question in the chat for Yann? And maybe Yann can read.
There are two interpretations here. Either I was super clear, or I was completely obscure and nobody isn't even able to ask a question.
There were a lot of questions during your presentation. So
okay. So what? You were clear. Thank you, Jean-Louis.
Yeah, it's true.
So the state implied in ondemand is also stored in the state structure along with memory. Yes. So if you have a stateful computation inside an ondemand, it means that you have a delay line. And this delay line is controlled by a time signal that depends of the clock of the on-demand. So every stateful every state will be unique to every different clock signal. About on-demand noise now being a function of how many times it has been called. Is that related to my question about on-demand noise now being a function of how many times it has been called? The semantics of on-demand of noise is the signal noise upsampled by the clock signal. This is the semantics of on-demand of noise. So it's the same noise, but upsampled in different way. So it's going to produce exactly the same samples, but with a but with the demand corresponding to each different clocks. Yeah,
so any other question in the classroom, or there's no question on our side? Maybe there is time for one more from the chat.
Previous song was a function of absolute input sample number. Yeah, So I don't know who is Ella Forge, but I hope that I answer your question, because it's always running. Yes, basically you can think that the previous version of Faust is like running into an on-demand where the clock is always 1. Yeah, so on-demand introduce a new thing to track. I'm not sure that I really understand that. What do you mean by a new thing to track?
Oh, hi, can you hear me?
Yes. Yes.
Okay, yeah. Sorry, I mean that that now these operations are a function of the history of how they've been used, right? Because they will only advance in time when on-demand is set. So that
Yes.
means for them to be, to know what they're going to be, you also have to know that history. But I would
Yes.
guess that because it all kind of, I mean, so Faust was already stateful, right? There's already delay lines and stuff, right? So presumably all that state is, it's stored in the same way, so if you have like a non-noise function, the noise will be a function of the input seed and previously the absolute sample at which you ask for it. But currently, how many times has on-demand been asked for? But internally, there's a table and an index into that table, or a computation and a seed in a computation that advances every time you ask for it. But at which point have you asked for it? That will be there will be a state value inside there somewhere that keeps track of where that is.
Yes, you can think the implementation as having a time signal. This time signal is it's just counting the number of 1 in the clock signal. And it is used in all the delay lines that are inside this particular on-demand. So again, the semantics is the noise generator as it was before, upsampled by the clock signal that you are going to use in the on-demand. So on-demand of a noise generator with a specific clock signal is the noise generated by the noise generator upsampled by the clock signal.
Okay, I think that maybe a way, if I can rephrase that, previously there was a single global time variable which advanced in
Exactly.
lockstep. But with on-demand, there are now possibly many time variables scattered throughout the individual ones, but it's just one extra bit of state stored along with all the rest, just like.
Yes, exactly.
Okay,
Exactly.
that makes sense. Thanks a lot.